Okay, and the topic for today is test coverage. So far, we've been doing a lot of lecture, learning how to write tests, even how to design your code to make it easier to test. Okay, but the question that you will have once you start writing tests is, when have you tested enough? There are many ways to answer that question, but today we will look at one quantitative way, try to measure, come up with a number that tries to estimate if you've tested enough. Before we even go into test coverage measures, what would be a very practical-minded way of saying when you have tested enough? What do you think people who don't do coverage do?
Test every method?
Test every method? But that's a coverage measure. So every method, 100% method coverage, that's one of the things we're going to look at. It's a good one.
They feel like it's enough.
Okay, you feel like it's enough. That's a good one too.
You're very tired of writing tests.
You're very tired. That's another one.
You can test the whole program as a whole.
You cannot test the whole.
Like test the whole program as a whole, like, and if it does what you expect it to do, then.
Okay, that's another way of looking at it. If you feel like you have covered all of the cases, okay, and one that you haven't mentioned is when the deadline is up. Okay, then you're done testing for sure. If your business team tells you we have to ship today, you're done testing. But you should not put yourself in that situation, and to try to even measure your way towards an ideal world of complete full testing. That's where test coverage measures come in. And here's the basic idea: code that you have not run in testing, it's likely to have bugs, or at least if you have some more time to do testing, maybe that's the code you should prioritize next. Okay, so that's one way to look at it. But this is very vague. What is code that has never run? Is it a method, like he said? Okay, that's one way to think about it. Is it a file that you've never executed anything in that file? That's another coverage measure. So essentially, by changing the definition of what is this code that you have not tested, you get different coverage measures. And that will lead to different numbers, try to quantify how much you've tested. Okay? So conceptually, you divide your program into elements, and this is intentionally abstract for now, elements, examples, statements, methods, files, and you define the coverage like a percentage, like this. The number of elements that your testing has executed versus how many of them there are in the program. If you get to 100%, then by that measure of coverage, you're done testing. So what we will do today is essentially looking at the advantages of considering various kinds of elements. Statement as elements, that's going to be the basic notion of coverage. And notice it's even more fine-grained than methods or files. I take that for granted. I mean, if you haven't really executed anything in a file, you have a big problem. I'm going to look more for, if you haven't executed a statement in your program. Next, we increase the level of sophistication. It's not enough to test every statement. You have to test every branch, every outcome of every branch. That's condition coverage. And then the fanciest I will describe is data flow coverage. This one, statement coverage, everybody measures. And everybody tries to increase, bring it quite high. Condition coverage, some tools measures. Actually, 10 years ago, this was a small number. Nowadays, it's almost becoming the norm. Data flow coverage, very, very few projects measure. So I am giving it to you because my thinking is that we're learning this stuff not just for what happens this year, but what to know, what's next if you want to, what's next in this direction. And so there will be a little bit of theory, if you want, of how these are measured, and I will have some screenshots from existing tools that show how these are reflected in your UIs and such. But first, we have to start with a 5-minute introduction to what is the structure of programs. How many of you have taken the compiler class 164? Okay, so those of you can come and teach this stuff, right? One of the things you learn in a compiler class is how does the compiler look at your program. So the compiler takes in a file that's a bunch of characters. It splits it into functions. Then each function is split into individual components, and it goes down to the smallest level is going to be an identifier or a string constant or a number. Those are the so-called literals in a computer program. But the compiler is going to build an internal data structure to keep all this stuff. And that data structure, at some levels in the compiler, is a graph. And so let's look at this program, and I'm showing you here what is the graph that the compiler puts this in. Okay, so we have a conditional, and this is the then branch. Oh, I should have put the braces here. But this is, imagine this is Python. Indentation gives you the scoping. So these two statements, then branch, this is the else branch. This comes after the joining point, after both if, then, and else, okay? So this is the graph that's constructed. So we notice that it is indeed a graph. Each of these red boxes is a node. The nodes contain sequences of consecutive instructions that do not have intervening control flow. What does that mean? You put several instructions in a block only when there is no way for control to exit the block prematurely, or there's no way to jump in the middle. So these two things will be executed as a unit, either both or none. They're both executed if this conditional is true. None of this is executed if it's false. Okay? So and this is the unit of many compiler algorithms work at this unit, at this level. And they can do very, very good optimization at this level. They can do somewhat less optimization at the whole graph, and even less optimization when you put all the graphs of all the methods together. Now, I'm not trying to teach you compilers, but this is a basic, fairly basic element of talking about your programs. Okay, and then the edges are the transfer of control. Control is essentially like how the program counter moves from this instruction to this instruction. So essentially, when I see something like this in my graph, this means there are two paths by which I can reach this statement. When I see this divergent, this is a conditional typically. So conditional switch statements are divergent. These are join points, and this is straight line code. Any questions about this? Okay, so let's remember this terminology. These are statements, individual statements. These are edges in the control flow graph, because we'll need that in the rest. So let's try to build together at least some part of the control flow graph for this function. So can somebody help me? How do I start? What's the first instruction that gets executed inside just the body of this function?
J is equal to 0.
So J is equal to 0. Next.
Checks if J is less than 2.
Next, checks that J is less than 2. Should I put this in the same block or not? I put two things in the same block if there's no way for the execution to abandon the block before the end of it, or for the execution to jump into the block in the middle. Is it possible for the execution to jump in between these two?
Yes.
Yes. How?
J equals 1.
J equals 1?
J equals 2.
So the execution comes back to here when you're done with one iteration of the loop. Okay? So I'm going to put this in its own block. And this is, I'm using different shapes for the blocks because this is a conditional that has two outcomes. So let's say that this is true. What comes here? J is less than 2. The comparison. X is equal to J. This is another block. And what if this is true? I'm going to trust you. And then what if this is false? It goes to the end of this conditional. So these things kind of join together, right? And afterwards they go to, what happens here?
J plus plus.
And then after J plus plus, I go to here. And then this is left over. And this is the return, right? So if I ask you to do statement coverage, then each of these count as a statement. And in fact, if we had more than one, if we had more than one statement in a block, we would count them separately. How many statements are in this program? Six? So statement coverage is going to be something of this form, something over 6. And then condition coverage, this is roughly the edge coverage. So how many edges we have? There's this edge here, 1. Actually, for condition coverage, we will measure mostly the conditionals, the outgoing edges of the conditionals. 1, 2, 3, 4. So condition coverage is going to be something with a divided by 4. So the way this works is you have a bunch of tests, and you want to measure how much are you testing. You run them all, and you keep track as you run them for this measure how many of these, which of these blocks got executed at least one in at least one test. And that number you put up here. It should be less than 6. For this one, you measure for each conditional and for each of the two outcomes of the conditional, which one got triggered in at least once in at least one test. So you take all tests together for this measure. Yes.
How come condition coverage is over 4?
Because there are 2 conditionals, each one with 2 conditions. So 2 times 2 is 4. So each binary conditional has 2 outcomes. The switch statement will have multiple outgoing edges. But I'm a little bit I just gave you an idea of where we're going with this. Let's take it a bit more slowly. So this is the graph that I wrote. It should be isomorphic with this one. It's just the different arrangements of blocks. And magically another statement came in here. Yes, I wanted to show that some blocks have more than one statement. So these ones would count as 2 for the statement coverage. Any questions on control flow graphs? Okay, so now you are compiler experts too. Okay, so we have, for this example graph, assuming that each one of these blocks contain only one statement, what would be a flow to the program to cover all of the statements? You start from A. Well, you shouldn't go to C, because if you go to C, then you cannot ever cover B in this test. You need another test. So a better test would be to go to B and come to C, come to D. This looks like a loop. This is the exit case and this is the iteration case. So if you come to D to have a really strong test, you should go to E at least once and then exit. Okay, and this is the shortest execution that covers all of the nodes. Is that clear? And sometimes you may want to write tests smartly, meaning what is the shortest test that covers what you need? I mean, for coverage, structural coverage, you don't need to go around the loop many times. Once is enough because you're covered, you're touching it. Here you were kind of economical by writing in one test covering all of these three. Does this test, so this is the test, A, B, C, D, E, back to D, and then F. Does this have all condition coverage?
No.
No, because this edge you have not missed. And that's okay. You can never expect one test to achieve full coverage. The point is you need multiple tests very often. There is also a notion of loop coverage. And for a loop to be considered covered, is you need to consider at least three situations. One is bypass the loop. That's a very important corner case that you should test. Second, you should go once through the loop and then multiple times through the loop. Because there might be a bug that doesn't show up if E is executed only once, but the next time you get back to E, something blows up. Similarly, there could be a bug in F that doesn't show up if you execute a loop at least once. Because when people write loops, most often they imagine that it runs many times, at least once, and they might forget the situation when the loop doesn't run at all, and that's often a bug. Okay, so let's look a little bit more in depth at statement coverage. Here, this is another example program. We'll use it for maybe 3 or 4 examples. So the interesting part is here. If x is not 0, then add 10 to x, and then divide y by x, store the result in y. And roughly, the control flow graph looks like this. I personally maybe would have added an explicit note for 5, but they didn't do it. And I got this from a textbook. It wasn't in there. But anyway. If our goal is statement coverage, and I tell you that you should have a single test that does statement coverage, give me an example of a test. And what I mean by that, a test consists on give me inputs, concrete inputs, and then the expected output. But maybe the expected output I'm not so interested at this point. Just the inputs that would make this program cover all of its statements. What would you pick? Somebody else further back. Does my voice carry through? So, what would you pick as an example of inputs, x and y, such that we cover all of the statements in this function? Over there in the back. X is not equal to 0. Maybe this was too easy of a question. So yes, and this is the example I picked. And this does have this execution, and it happens to have this output, and you plug this in the test, run it, assert that the output state x and y is the same. But so the coverage, statement coverage so far is, it's a good number, 100%, okay? So if your manager says, go write tests until you have full statement coverage, you are done. And you bring this statement coverage tool output, and it shows this. But now I'm going to ask you to, just trying to see where I'm going with this, are there still bugs in this code?
Yes.
Like what? Or they are very enthusiastically saying yes.
You can't divide by 0, and this is kind of setting you up to divide by 0.
Okay, 0.
So there's a potential for a problem here, and the way the code is written, it doesn't protect it enough against it, okay? Yeah, so I'm gonna get back to that. But one thing that you should remember from this lecture, and I'll repeat this probably 3 times, is code coverage is a good tool. It does give you a number, but don't take it, too seriously. When it's 100%, it doesn't mean that you have 0% bugs. No matter what code coverage measure you will pick, there still can be bugs hiding that go beyond code coverage. But before I go to more sophisticated code coverage measures, let me tell you what the status is. Everybody uses statement coverage. Everybody is serious about doing testing and code quality. But it's not as easy as it was on our previous slide. Pick one example and you're done. So Microsoft reports about 80% to 90% statement coverage in their tools. Does this seem high or low to you? Risky.
Reasonable.
Oh, reasonable. Okay, you're saying, what do other people think? Well, clearly Microsoft is not ashamed to have leaked that number. How big do you think Windows is in terms of lines of code?
100 million.
100 million? Last time I kind of knew about these things, it wasn't Windows 8. It was more like 40 million. But, at the rate they're writing code, probably it's 100 million. I doubt it, though. But let's say many millions, okay? Let's take this smaller number, 40 million, because it's going to make Microsoft look a little bit better. Times 20%. This is lines of code they have not executed. They gave you Microsoft Windows without executing. How many lines is this?
8 million.
Can you imagine? You're running 8 million lines of code that presumably they haven't executed. It's a lot. Okay? So this seems like a low number if you look at it that way. But Microsoft is going to come in and say, oh, well, that 8 million are never going to run on this machine. It covers cases that you're never going to worry about that or whatever. Or maybe that 8 million lines of code, actually maybe, let me ask you, what do you think is in those 8 million lines of code?
UI stuff.
UI stuff? But that presumably they have run. But maybe they haven't measured properly. Okay, so we'll talk a little about how this is measured. What else do you think there is? Comments. Good, but Microsoft should not really include the comments. So comments are, so sometimes you see this code metric, NCLOC, non-comment line of code. Okay, so we'll just take the comments out of the picture. Non-empty lines, we take the empty lines out too. What do you think is there?
Contingencies for all the weird, very hardware that Windows is supposed to be able to run on.
Okay, so just corner cases for various environments. Yes. So maybe they haven't really tested all combinations of hardware. Something else?
What about auto-generated
code? Auto-generated code, that's a good one. Yes, I suspect they have a bunch of that. In fact, I'll have actually, I just looked before coming to class and said, I should measure the coverage of my tool. What is it? And I saw a thing that was 50%. So, oh, wait a minute, what's there? And it's auto-generated code. Good. The other things that are hard to test.
Outdated code?
Say it again?
Outdated code?
Outdated code. Code that's not really used anymore. So I'm sure they have 1 million at least lines of code that was there at some good point, useful, but it's not used anymore. Anyway, there are all these reasons why you have. But if you go to NASA, they will never send the shuttle up with that kind of coverage. So in fact, NASA and people writing medical devices and some of the code in an airliner has to be written. There's a so-called, I think it's called the Red Book. It's a book of standards for how you should write code that's used for in where somebody's life depends on it, essentially. And there you have to get to 100% statement coverage. There are many projects that have only 80% coverage. And going above 95% is actually very hard. It becomes increasingly hard to get to the top of this mountain. It gets steeper and steeper. Why do you think that people stop testing when before the coverage is 100%?
It probably mostly works most of the time. If you're getting that kind of coverage on your executions of your tests, it's probably doing most of it correctly as far as you can tell.
Yeah, so it probably is mostly correct. I agree. If those 80% are the good 80%, the important 80% of your software, then probably you're doing a good job. Yeah, but you have to believe that they use multiple ways to measure how when they're done, and maybe something else tells them that it's a good time, and we'll talk about some of that. But let's move on to say, what if you want to do more than statement coverage? Okay, so I'm not kind of changing gears a little bit, because on one hand I'm saying it's hard to achieve in huge projects even 100% statement coverage. But what if you have a portion of your code that you're particularly worried about? It's your model, data model. It's the one that assures the integrity of your data. Okay, if you have a bug in the UI, you can survive that. But the bug in imagine a bank's models and database management code. If they screw up numbers down there, the UI could be correct. It's going to show the wrong thing. So what can you do? What are more sophisticated measures? So just to review the statement coverage, this was our test. This will cause coverage so far. And you already pointed out that there's a bug that's not covered. And to reveal this bug, it turns out that to actually trigger a divide by zero here, you must come if x is 0, you come from 5 to 7, that will trigger the bug. So it just happens, in this case, that if you find a test that executes at this edge, they'll trigger the problem. You agree with that? I think so. So this is trying to motivate the next measure, which is more like edge coverage or condition coverage. And this is actually something that people nowadays use a lot. This really has changed in the last 5 to 10 years. Condition coverage has become almost as standard as the statement coverage. But it's a little bit tricky to define. Some people say, oh, if I touch this if statement, I'm done. But that's not the right way of thinking about it, because an if statement has two behaviors. You have to really test both behaviors of each condition. Or if it's a switch statement, all possible outcomes. So I'm going to call one of these outcomes of a branch a condition true or condition false for each branch. So you take number of conditions in the program, typically is the number of ifs times 2. And these are the ones that you have traversed in at least once in at least one test. Okay? So both a branch is considered covered when you've tested both conditions. In the reading that you have online, which is a very interesting reading, and I wanted to read it. It tells you the good and bad of code coverage. They refer to this as multiple condition coverage to really stress the fact that you're trying to address both sides. So let's see how this works. So you cannot do, for this program, condition coverage with one test, because that one test either is going to go this way or this way. So you have at least 2 tests. And this is your test suite. And this happens to find the fault at line 7. Okay. So that's really it about condition coverage. I think there's nothing more to understand. Let me switch gears now a little bit. Do you have any questions about this? not. I want to switch gears from the theory more to the practice. There are many tools that compute code coverage, and most tools come with nice UIs. Some of them, they have just the data collection part, and you have to kind of grab to it. So this is an example. I'll be zooming in a bit, but I just want to first give you the overview. This is an example of a UI that people wrote. It's called Lcov. This works in conjunction with the GCC suite, the C compiler suite, Gcov. So when you install GCC on your machine, in fact, unless you have Windows on your laptop, you have GCC probably already there. And it comes with this program called Gcov, which computes coverage measures. By the way, let's take a little bit a detour here, since you are now you like compilers so much. How do you think these numbers are even calculated? Like the number of statements that I've executed in this suite. I want more of you to think about this. How can you find out? You have this program, you have these tests, you want to run all the tests, and I want the number of statements that I've executed, I want the number of branch conditions that I've executed, I want the number of total statements and total branches. Let's start with the easy one, total statements and total branches. This is easy. Oh yeah, easier. The number of lines in your program. Have you done this ever for your programs? Count? Yeah, it's a text file count of sorts. Okay? So WC does word count, WC-L will count the files. There's scripts that do this for you. Okay? These are called static measures because they count things about the structure of your program. And remember, I told you the compiler reads your program, constructs this graph. It's a very easy algorithm to traverse that graph and count the nodes, count the edges. Okay, so that's easy. That's what I was hoping you'd say. But the more difficult question is, how do you count which of these edges get executed? So two of you have some. Says, I want more of you to think about this. How would you solve this problem? Now that you think it's very useful. Okay, I'll pick you.
You could put every possible input into the program, and then see how many times certain statements get executed.
But actually, the question is different. The inputs are already picked. You have written your tests. And I want to count the second part of what you said. How do you count how many edges got executed? When I run to all of my inputs.
You can set breakpoints in the code, or at a very primitive level, you just have print statements on different parts of the branches that will display every time they.
But that's the idea. Except nobody's gonna go put in 40 million lines of code print statements. So the compiler will do it. So GCC has a flag. Forgot the exact flag. Say add coverage information. It will compile a print statement of sorts in crucial places in the code. Not at every instruction, at the beginning of a basic block maybe, at the outgoing edges of a conditional. And these are not going to be print statements that show up on the console. They're going to use some internal data structures to mark a bit that this statement was executed. And this is all kind of very elaborate, very low-level algorithm. And your program will run a little bit slower if you turn on the coverage. But at the end, this data structure gets dumped. And if you use GCC, it's going to dump some binary files. And then Lcov will read them and map the line number of each one to the actual source code and display this. Okay? There's no magic in computers, okay? So you should, I mean, I keep asking you, how is this done? You should ask yourself always, how is this done? So let's look at this, and how would you interpret this? So this is a zoomed in portion of the slide. So look at the display. On the right side of the page is your text, is your source file. Here, there are some counters. These are the statement coverage counters. This means that this line got executed 3 times. 3 of your tests got through here. Or maybe one test called this function 3 times. This line got executed 67,000 times. Well, how is it possible? Probably because you went around the loop tens of thousands of times. This line, this is the body of the loop, got executed. Do you see the numbers? This is 48, this is 46. Okay? So, can you explain to me how come if this for loop was executed 67,000 times, the body of the loop was executed 2 times fewer?
They had to do one for like the actual like what's it called? You check them in, and then sorry, we check the conditional, and then an extra, another one for the assignment. Or does it not work that way?
No, actually, this is this reminds me. I should clarify. Some tools are not very precise about what they count. This one, let's say, counts lines. As long as you executed something on this line, and there are 3 statements on this line: the initializer, the conditional, and the increment at the end. This counter will get implemented every time. Okay, so this is line coverage. I should be clear. You see, it even says here it's lines that is measured. But how come your execution got on this line 48 times and on this one 46 only?
Because the last time in the loop, the conditional failed, so I'll check the conditional for everyone. See if it's in the loop.
Right. So 2 times when I got here, I bypassed the loop because the conditional checked false. And actually, look, magically, there's a 2 here at the return statement. Okay, so that accounts for the 2. How come this is 46 and this is 45? There's an exit which got executed once. This also explains why this is a 2 and this is a 3. I got 3 times through here, but only 2 times I exited through here because once I exited through there. Okay? So these numbers do make sense, and actually, looking at them a little bit, sometimes you understand the scenario that didn't get executed. Say, oh, I never got here because, and that kind of gives you an idea of another test to write if you're worried about this. On this first column, it shows branch coverage. There are 2 branches in here. One is this loop termination condition, and the other is the if in the body of the statement. And it puts a plus for the then branch and the else. When the condition was true, when it was false, true, false, and so on. Okay? Clear? And let's here at the top, I should have started with this. This is a perfect example. Coverage of lines, 100%. Coverage of functions, 100%. Coverage of branches, 100%. And notice that the branches are counted as 4, even though there are only 2 really, because they count both outcomes. Okay? More colors. Okay, can we move on? Okay, more colors. This is another tool. This is so Lcov is a kind of free tool that you can easily download. This is a commercial tool that comes from Atlassian. Atlassian is a builder of general productivity. They build Jira, I think. Jira is like an issue tracker system that's really professional grade. They build Confluence. Confluence is like a document management system. So we use Confluence at Conviva for writing documentation and sharing all that, and we use Jira for our issue tracking. And they have this code coverage tool. And there's a lot of stuff on this page. Here at the top, there are statistics about how big this project is. Non-common lines of code, 21,000. So it's a kind of already a medium-sized project. This tells you some overall, coverage, 62% coverage so far. This tells you the test results, 786 tests, and notice the time, 13 seconds. I would classify this as a well-written test suite because they probably use mocking a lot. If this code even accesses external services, maybe it's all kind of algorithmic code, and then it's easier to achieve that. But this is what you should aim for, things that run in under a minute. I'll get to the colors last. This shows you a histogram of how many classes in various coverage buckets. So this many classes have 100% coverage. And there are some classes with very little coverage. And then there are some classes with 0% coverage. What do you think is going on here? Why do they have so many classes not covered?
Libraries?
Libraries. They probably include some libraries of which, these are jar files that maybe have more classes than they need in their project. So that's not necessarily bad, and otherwise they would have fixed it. Maybe from here they only need certain methods from certain libraries, and even that might be okay. It's not always a bad sign. This is another plot chart which has coverage on the x-axis, 0 to 100%, and then complexity. There's various ways to measure code complexity, like conditional complexity, loops, and generally you want complex code up to be high coverage, because that's where you feel your test might be. So the worst would be a point here. Low coverage for very complex code. Okay? This is very simple code, the easiest to test code probably also, and of course it has the highest coverage. This is the low-hanging fruit. Right? So that's where programmers go because that's easy to test. A few daring ones went and achieved high coverage for complex code. Okay? So this is probably typical of what you see in projects. And this is another way to show the same information just differently. The size of the box gives you the complexity, and the color is how dangerous, how little coverage there is. So you have, this is small classes, so small complexity classes that are not covered. This should be low-hanging fruit here. Okay? A wealth of information. The least tested methods, most complex packages, you can spend all your spring break with this, of course. And this is just a coverage tree map of the entire project, kind of structured by packages. And since we're still into pictures, I picked another tool. This is a Google coverage tool. They use it internally at Google. And they actually publish the internal test suite for Juice. Remember Juice from last lecture? It's a framework that Google wrote for dependency injection. And they wrote tests for the framework. So you write a testing framework, and then you write tests for the testing framework. Because it's software. It has bugs. So it needs testing. But what I wanted to show here is two things. First, red is stuff that was not covered. And this is a very typical thing that happens. This is a conditional that's red because it's not covered. And if you notice, I hope you can see the numbers from the back there. This was tried, executed 94 times, and 0 times the conditional tested true. So that's why the conditional is marked red, because all the 94 times it went false. And this is a null pointer exception, okay? It's hard to test the error cases. And you really, in the first stage of testing, most people test the normal execution cases. It's hard to get to the error cases. But what I like about this tool, not every tool has this. You look at this coverage report, and you say, look at this line. I want to test this line. But it might be hard for you to even think how to get there, because this could be down deep in the guts of your program. What you can do is you can click on the line above and say, well, some tests came very close to it. They came to this conditional. They just came with the wrong condition. And you can click on this line and say, give me the tests that came here. And that's where this pop-up comes. This is a pop-up that's on top. And it says that these tests, all passed, came through the particular line. I think it's 648, this one that I tested. But it's probably the same as the one above. And what do you think you could do if you have this information? Which tests executed this conditional?
Modify the test.
That test, one of these tests with a small mutation, can probably give you the test that you need. Because it does almost, and it comes very close. So you can find a way to tweak the test to do almost what it was doing before, except coming with the entry equals null. You might be done. I do this all the time. This is how you write tests, you compute coverage, you look at the coverage results, say, I want to test this. Well, what's the test that came closest to it? And then I think about it, say, oh, I know how to I make a copy of that test, or sometimes I just parameterize the test and call it with two different arguments. Let's take a break now. And in the break, I have a brain teaser for you, and there's a choice actually of brain teasers today. There's one that's computer science-y, and then one that's more logic with hikers. You want outdoors or indoors, brain teaser? Indoors. Well, he was the first one to ask, so I'm going to give you the indoors one. Okay, so I think you understood statement coverage, hopefully, condition coverage too. I do have some more examples here to try to motivate that even this is not perfect. So the first test case, x is not 0, so it goes in here. Y is greater than 0, so it goes here. So that's the path that follows. And the blue test case, it's chosen carefully for every conditional to follow the other paths. So this is a very economical way to cover not just the statements, but all the conditions. Okay? But this is not always the best to just try to minimize the number of tests, because even here, you notice that there is a possible bug. Again, I'm kind of looking at this division by 0. For this z to be 0, I can get this z to be 0 if I come through here and then take this path. But because I chose my test, I'm getting this 100% condition coverage, and I'm not really covering some important behavior of the code. Right? It's important to remember that code behaviors are infinite. Number of conditions, number of statements, numbers of files, numbers of anything in your program is finite. So you cannot hope to characterize an infinite number of program behaviors with any choice of counting finite elements in your program. Okay? But condition coverage is still, useful. Yes, but it does not reveal a default at line 10. And for this one to be revealed, you need a different kind of coverage. And luckily, there is such another coverage. It's more sophisticated than branches. And let me explain what is the... Let me see, do I have it on the next slide? Yes, I just draw it. I zoomed in into that graph to show that what you need is to somehow execute this statement with a definition of z that comes from here, not from there. Okay? Because if you look at it, where could z be computed? The z that's used at line 10. Well, just go backwards in the graph, and you see that these are the two possible ways to compute z. Okay? The truth is, it's still possible to compute a z equals 0 from there. If you come up with x is negative 10, but at least just looking at syntactically, if you were to try to count all the pairs for every use of a variable like y and z, how many lines compute that value? and make sure that you have a path that follows that flow. Okay? So this is called a data flow coverage criterion, and it's a data flow in the sense that the data follows from line 8, which defines Z, to line 10. And there's another data flow from line 6 to line 10. Okay? Data flow is a more advanced notion of compiler analysis, actually. Many of the optimizations, if you turn on -0, 2, 3, and 4 in GCC to optimize your code, it's going to compute data flow and it's going to do fancy optimization based on these data flows. And code coverage tools essentially have borrowed the idea. And the idea here is to count these kind of virtual edges in your program, which is flow of variables to actual uses of variables. I'll go somewhat fast over this, and I will not include it in the midterm. I want you to have a sense of what it is. It's a very advanced technique. Really, only very sophisticated software houses use it, and they only use it for a small portions of their code because it's actually more expensive to compute. Okay, so this is also called a def use coverage. Def stands for, it's an abbreviation for definition. All of the statements that assign to variables are definitions of those variables. This defines the new value for Z, this defines the new value for Z, this one for W. So these are defs, 2 defs for Z, 1 def for W. These are defs for X and Y, defined by reading some input from somewhere else. Uses are reading the value of a variable. X is used here, X is used here, Y and Z are used here. So you take every variable in turn, and for every variable, you list the pairs of a definition and the use where the definition can flow. X, let's take X. X is defined here, and this definition flows here, and where else does it flow? What's another use of X that's defined there? 6. Okay, so these are the 2 def use pairs for this definition of X. Still looking at X, well, there are no more definition of X. So we're moving on to the next variable, Y. You take every definition of Y. There's Y there, it flows there, and where else does it flow?
10.
10. Okay, and we're done with Y. And now we have Z. We have 2 flows of Z. And essentially, you are done. And notice that the incoming edges, this tells you the uses here, where they come from. So there's a use here that comes from 6. That's a use of Z. This is a use of Z. This is a use of Y. Okay? And the idea is that you should run tests that cover all of these edges. There should be a test that follows this edge, for example. It comes from 4 and gets to 10. There should be a test that comes through 6 and 10 for this edge. There should be a test that comes from 8 to 10. And that's going to trigger your error. Okay, so this is the def use. But it's the same concept. Once you count them, you instrument the code to count them at runtime, how many of them are executed, and then you divide by this. This is, I'll just leave this for your, it turns out that 2 test cases are needed here to cover all of these def uses. And this actually reveals the fault. But notice that I'm not covering one of the branches of the conditional. So this is actually fairly typical. You go to more and more sophisticated coverage scenarios. They are not subsuming each other necessarily. They can find more bugs, but sometimes you need both 100% branch coverage and 100% def use coverage, or some compromise thereof. Let me just move on. I want to move on to this part, which is coming to thinking about all behaviors in your software. Not because you're going to be measuring this, but because you should be aware that software is actually very, very complex, can be very complex. So first, I want to tell you and convince you that the number of paths in a program can easily be exponential in the size of a program. Okay, so imagine that you have a program with a sequence of n if-then-elses. Each one of these is an if-then-else, if-then-else, one after the other. Okay, this is not so unusual. Maybe they don't quite look like this. Maybe they do some more computation in here, but it's like this, right? So you count n, and the number of behaviors, combinations, could be 2 to the n. Okay, so you cannot, I mean, when you have exponentials, I mean, you cannot hope to do any sort of exhaustive algorithm. But for simple but critical pieces of code, this is what you should actually be doing. Some of the paths sometimes are not feasible. Like this is actually fairly common pattern. You start your code with a conditional, testing a special condition. Is this MySQL or Postgres that I'm using? And then you set up some variables. Then you do your work, and then you have the same conditional. Is this MySQL or Postgres? And you do some cleanup that should match. Okay. So yes, there are two conditionals, but only fewer of the paths are feasible. Okay. So you should only really test the feasible paths. Okay, so for this example here, we have two conditionals, if then else, and another if then else. So a quick calculation tells you that there are 4 possible paths in here, and you should have a test for each path. So 4 tests, and this one, this test is going to hit the assert false. So you're happy, you caught the bug. What else? What other kind of coverage criterion is going to ensure that you hit any assert false? Condition, and even statement coverage. For something to hitting a bug like this or a statement like this, even statement coverage will catch it. Have you ever written code with assert false? You did?
Yeah.
Why?
It was the condition was checking to see if the test passed, and the best way to express it was to assert false with some explanatory error message.
Correct. So I also use this quite a bit. Sometimes the other way to do it is to assert y is greater than 0. But sometimes it just works the conditional such that I write this. So this is a way of writing an assertion in the code saying I should never get here. If I ever get here, let me know, and I'll scratch my head and find out what I'm missing, because you should never get there. You run test coverage for this. If your code is correct, it's not going to be 100%. There's no test will come here. Okay? Same for condition. This condition will never be false. Okay? So sometimes 100% coverage is not even theoretically possible if you have a code like this. But exponential number of paths in acyclic code. If you have cyclic code, forget it. Okay, this code you can count. Okay, it has. It's not even easy to count, but it goes around the loop 2 times, and in each one it can do this conditional, whatever. It's actually quite tricky if you try to count how many paths there are to that, because J changes. But a finite number of paths. This one has a finite number of paths once you fix n. But if n is an input, it's just as good as n. And then if you have many server loops are written with a while true, keep going, that has an infinite number of paths to the program. So I do want to speed up a little bit. The point that I'm trying to make with this slide, and just try to remember the high level bit, is no matter what structural coverage criterion you pick, there are still possible, and you reach 100% of coverage of that criteria, it's still possible that you have bugs that are just not covered. So that's lesson number 1. I think it's not this one. But there's other ways in which coverage can be misleading. Look at this code. You perform this operation. You look in the man page for that function, and it says that fatal error could be one of the return code, and you write this code. You run your tests. Your tests come out as this line is not covered. You scratch your head, and you write maybe a mock or a double for this operation to make it fail with fatal error, and then you have a test that covers this, and you're happy. But what if you misread the manual, and the manual says that both fatal error and very fatal error can be returned? Okay? You forgot to write a conditional. Code coverage will never tell you that you forgot to write code. It only measures for the code that you wrote, do you execute it? And it doesn't measure the code that you forgot to write, the cases you forgot to handle. Okay? It tells you about the cases that at least there's a conditional in the code. But if even the conditional is missing, like if status equals, uber fatal, then something, that's not going to be caught. So keep that in mind. That's kind of bad. So I do want you to use code coverage, but use it with a grain of salt, because 100% code coverage doesn't mean lack of bugs. We've seen many ways in which code coverage can bypass bugs. Plus, 100% code coverage is almost never achieved. It might not even be economically feasible. Okay? How do you use it, though? It's not perfect either way. Having 100% is not good. Getting to 100%, it might not be economically feasible. Run code coverage and at least inspect the output and scratch your head and say, why is this lower than I think? Or I think I wrote enough tests for this suite. It should be covered. Okay? So when you see low coverage, you have to make a judgment. Should I add a test here, or maybe no? This is really such a corner case that it's not worth covering. So I told you that before coming to lecture, I opened my project, and this is PyCharm. It's so easy in PyCharm to set up, and this is the same in RubyMine. You set up a test scenario. This runs all my tests. It's very easy to set up, and I have a lot of tests. So this was, it's a fairly big software system. Well, it's 100,000 lines, including front end and back end. But I've written it from the ground up with test-driven development. I always wrote the test infrastructure first, test fail, then fix the code, and keep going. And always when somebody reports a bug, I fix the test. And this is one of the modules. So I go up here. Client gate, this is a portion of my software that I believe is very highly tested. And I look at it, and it says 55% line coverage. What is going on? Because I thought that's covered. So I go in it, and I see that most of my files here are, look, some of them are 100% of the lines covered. And the lowest one is at 85% and up. So, but what happens, there's this PB directory with auto-generated code by a compiler. And the compiler is very generous when it generates code, this compiler. So it has some methods in there that my code doesn't actually use, right? So then I can go to one of these, say, okay, 86%, what's not covered? And it shows in this panel here. Why don't I see? It takes a while, and you can barely see the coloring here, green and red. So I look at the green, at the red, what I don't cover. So there's this strange case. Many of these are error cases that I haven't. This is a type checking code. In my Python, I did some type checking to make sure the type is correct. It's like an assert, and I never had a test case for that. So most of it is green with a few components. The other thing I wanted to show you, since I just have a few seconds left, I also did, just for my fun, when the coffee breaks, I wrote a little script to count how many lines of code I have in my project. So there's a total of 64,000 lines of Python. But then I said, how much testing code did I write? So my script goes in every file, and I have a certain structure of how I write my test that the code can recognize. But generally, I have metrics and metrics test, LPG and LPG test, heartbeat Q test. These are tests. So if you look at, and then I compute what percentage of the, so I have, it's not really 64,000, it's 52,000 non-empty lines and 16,000 test lines. So 32% of my code is test. I think maybe half of my effort has been writing the test and all the mocks that I need. But it's really worthwhile. And then I have 8,700 JavaScript, 2,800 CSS, 36,000 HTML. This is I have tests, but are not measured here. And to me, this is the best project that I wrote in terms of code. So this is actually a product. This customer is using it. Moniva is actually selling it. And I'm the only developer that built it from scratch up, and I maintain it part-time. And it runs 24/7. Okay? So because when somebody comes and gives me a bug report, even though I only have 15 minutes between a lecture and a meeting to fix it, I fix the bug, run all my tests in a minute or two, and I have fair confidence that I didn't break anything. And to really make it even better, I have a deployment strategy.